My name is Thomas Diem, and I'll be talking about Section 9 in the Calculus textbook, which includes the topics of differential equations, Euler's method, and logistic equations used to model natural growth. Let's start with reviewing how to graph differential equations using slope fields, which should be reviewed from Calculus AB. For example, a problem may ask us to graph the differential equation y prime equals 1 over x plus y, with the initial condition that y of 0 equals 1. We'll start by setting up our graph. For this problem, 2 coordinates in each direction of the origin should be sufficient to get a decent idea of what the graph looks like. Remember that y prime represents the slope at any given point, and y and x represent the coordinates of that point. So for example, if we plug in the point 1, 2 into this equation, then x equals 1 and y equals 2. So y prime, or the slope of the equation at that point, equals 1 over 1 plus 2, or 1/3. So we can use this information in our graph to show that the slope of the equation at the point 1, 2 is 1/3, and graph a tick mark with that slope at that point. In a similar manner, we can plot the rest of the slopes at each point in the graph. We plug in the x and y values to find y prime, which is the slope at that point. If you want to go faster, you might start noticing some patterns in the graph, like whenever x is equal to negative y, then y prime is 1 over 0, or a vertical slope. Now we want to graph a line that goes through the point y of 0 equals 1, or 0, 1. So to the best of our abilities, we graph a line that follows the slope of the tick marks that it goes through, starting at the point 0, 1. In the end, we get a graph that looks something like this. Remember that these slope field graphs are never perfectly accurate, but they are good representations of the graphs of differential equations. In some differential equations, we can separate the variables and solve the equation by eliminating y prime. For example, a question might ask us to solve the differential equation y prime equals e to the y minus x. We can rewrite y prime as dy dx, since they mean the same thing, and writing it as dy dx will help us separate the variables later on. Our goal is to have all the x's on one side and all the y's on another, so we should start by separating the variables on the right-hand side of the equation. By laws of exponents, we can rewrite e to the y minus x as e to the y over e to the x. Now we can manipulate the terms in each equation to have all y's on one side and all x's on the other side. In order to eliminate the dy and the dx in the equation, we can take the integral of each side of the equation. This is mathematically legal because we know that the two sides of the equation are equal to each other, so their antiderivatives must also be equal. We can rewrite the equation so that it's easier to integrate. Now we can integrate both sides of the equation. One common mistake is that students forget to write plus c because we are integrating. But it should be noted that we just need to write plus c on one side of the equation, since it represents any constant, so putting it on both sides of the equation would be repetitive. We can now multiply both sides of the equation by negative 1. Writing minus c is the same thing as writing plus c, since c is not a set constant, but instead any real number. A lot of students make the mistake of thinking of c as a fixed number, but it's important to realize that plus c and minus c are the same thing. Now we want to isolate the variable I, so we take the natural log of each side. Our last step is to multiply each side by negative 1. We get a final answer of y equals negative ln of e to the negative x plus c, which can't be simplified any further. Another section that's covered in Chapter 9 is Euler's method for estimating values in a differential equation. Suppose that a question asks you to approximate y of 0.3 for the equation y prime equals x over 2, with a step size of 0.1, starting at y of 0 equals 1. Euler's method uses tangent lines to estimate the values of the graph, using multiple steps in each problem. For this problem, we are going from x equals 0 to 0.3, using step sizes of 0.1. So to solve this problem, we would first use the tangent line at x equals 0 to estimate the y value at x equals 0.1. Once we know the y coordinate at x equals 0.1, we can use that to find the y value at 0.2. We can then use the coordinates to find the y value at x equals 0.3, which is our final answer. The red line in this graph shows the equation y prime equals x over 2, with y of 0 equals 1. We're going to use tangent lines to estimate the y value at x equals 0.3 of this graph. The blue line shows the tangent line to this graph at x equals 0. As you can see, it is very accurate for values close to x equals 0, such as x equals 0.1, but it is not as accurate for values such as x equals 0.3. So we continue by using another tangent line, this time starting at x equals 0.1. We can see that the yellow tangent line is more accurate for values closer to 0.3. Now we graph a third tangent line, this time starting at x equals 0.2. As seen in this graph, the green tangent line gives the most accurate estimation of x equals 0.3. Now that we understand this concept, let's try to solve this problem without using graphs. We'll start by estimating the y value for x equals 0.1, or y of 0.1, which is the first step of this problem. To calculate y of 0.1, we set up our equation as the y value of the previous term, y of 0, plus h, the step size, in this case 0.1, times y prime at the previous point, so y prime of 0 in this case. We can now plug in values and rewrite the equation. And we solve and get a final answer of 1.1. Another, perhaps easier way to think of this is that we are creating a tangent line at y of 0, and we are using it to find y of 0.1. The equation for our tangent line would be y equals m times x minus x1 plus y1 from our point slope form. M is the slope, which would be the same as y prime at the point 0, 1. Y prime at this point is equal to e to the 0, or 1. Since we are using the point 0, 1, x1 is 0 and y1 is 1. We can simplify this equation and we get the line y equals x plus 1. Now we want to find the y value at x equals 0.1, so we simply plug in that value. And we get the same answer that we got earlier. Now that we understand why this formula works, let's continue and solve the rest of the problem using the same method. Y of 0.2 equals y of 0.1, the value we just found, plus 0.1, the step size, times y prime of 0.1, 1.1, or e to the 0.1 over 2. We can then simplify this. And using a calculator, we estimate y of 0.2 as approximately 1.205-12711. Now that we know this value, we can use it to find y of 0.3, which is our final answer. Y of 0.3 equals y of 0.2 plus 0.1 times y prime of 0.2, or e to the 0.2 over 2. We can simplify this equation and plug in numbers. Using a calculator, we get a final answer of about 1.315644202. A second part of this problem might ask us to determine if the value is an underestimate or overestimate of the real value. We can figure this out by determining if the equation is concave up or concave down at the value x equals 0.3. We do this by finding the second derivative. We know that y prime equals e to the x over 2, so y double prime is the derivative of that. We take the derivative and get y double prime equals 1/2 e to the x over 2. If we plug in 0.3 for x, we get a positive value, which means that the graph is concave up for x equals 0.3. Therefore, the estimate found by Euler's method is an underestimate because the slope of the graph is increasing. So the tangent lines, which have a constant slope, are going to end up yielding lower y values than the actual graph as the x values increase. Now let's talk about logistical equations and how to use them to model natural growth. To understand this concept, let's start with a sample problem. This problem asks us to suppose that a species of fish in a lake is modeled by a logistic population model with a relative growth rate of little k equals 0.3 and a carrying capacity of big K equals 10,000. In part A, we are asked to write a differential equation describing the logistic population model for this problem. You might remember that the differential equation for logistic growth is written in the form of dp over dt equals kp times 1 minus p over k, where p is the population at a given time t, big K is the carrying capacity, which in this case is the maximum number of fish that can live in the lake, and little k is the relative growth rate, which doesn't have a tangible meaning in the context of the model, but it is needed to complete the equation. A common mistake that students make is that they confuse big K with little k, which are two completely different variables. We can solve part A in this problem by substituting variables in the equation, since they are given to us. Our differential equation is written as dp over dt equals 0.3p times 1 minus p over 10,000. Part B of the question asks us to suppose that 2,500 fish are initially introduced into the lake. It asks us to solve and find the analytical solution p of t that models the number of fish in the lake after t years. We then need to use this to estimate the number of fish in the lake after 5 years. The first step of this problem is to write a setup for the analytical equation, that is, an equation without dp over dt. This can be derived from the formula in part A of the problem, but it is much easier and faster to memorize the setup. The equation is written as p of t equals big K over 1 plus a times e to the negative kt, where big K is the carrying capacity, little k is the relative growth rate, and a is defined as k minus the population at time 0 over the population at time 0. So to find k, we use its definition and plug in values. The carrying capacity is 10,000, and the initial population is given to us as 2,500. We simplify this and get a equals 3. Now we can plug in this value and the known values for big K and little k into the equation. The second part of the question asks us to find the number of fish in the lake after 5 years. To do this, we simply plug in 5 for t. If we plug this into a calculator, it will yield an answer of about 5,990 fish, rounding to the nearest whole number. Part C of this problem asks us to use the model in Part B and find the time it will take for there to be 8,000 fish in the lake. We can set up our equation as 8,000 equals 10,000 over 1 plus 3e to the negative 0.03t. With a graphing calculator, you can plug this equation in and solve for t. You'll get an answer of t equals about 8.283 years.